Alright, problem 1b, a little trickier than 1a. Our goal is the same. We'd like to write the general term for this series, and we need to decide if this series is geometric or not. If it is, we have some more work. If it's not, we will be done, but we'll need to be able to explain why it's not. So remember what I've said sometimes before. It's sometimes useful to list out the term numbers when trying to recognize a pattern in a sequence or a series. So I'm going to call those my term numbers, which is n, and then this will actually be the value up there of the term. So also another idea is that it's sometimes useful when you're dealing with a sequence or series that has fractions to look for a pattern in the numerator and then look for a separate pattern in the denominator. So let's start with that. First off, for whatever reason, I'm going to start with my denominator because I look at these numbers and it doesn't really look like it makes sense to me, but then if I kind of cheat a little bit and make those fractions also, we can only put them over 1. That's really our only option there. But let's see if we can recognize a number. 1, 1, 2, 6, 24. Maybe that's a pattern you recognize since we've seen it before. Maybe you don't remember it, but maybe you remember it from when you did probability last year. That looks a lot like a factorial. 1 times 1 is 1, 1 times 2 is 2, 2 times 3 is 6, 3 times 4 is 24, 4 times 5 is 120. I bet you that's going to be the next denominator there. So you can see that each time we're multiplying by one higher number than before, we need to use a factorial if we want to represent that mathematically. So let's again compare this to our term number, because if, for example, say if we wanted 6 factorial, that's going to be 6 times 5 times 4 times 3 times 2 times 1. Well, we need to see where does that line up with the way our sequence is laid out with our values of n. So, by which I mean that first term there, well, that's like 0 factorial. Second term, 1 factorial. Third term, 2 factorial. Fourth term, 3 factorial. Fifth term, 4 factorial. So you can see each time that the factorial that we're doing is 1 less than the term number we're at. So that's like 5 minus 1 factorial. That's like 4 minus 1 factorial. 3 minus 1 factorial, yada yada that way. But in this way, that means we're dealing with n minus 1 factorial for our denominator. So I'm going to go ahead and just put that there right for now because we know that's true. Now let's look at our numerator. The numerator pattern is easier to see than the denominator. Notice that it's increasing by a power of x each time, but also notice that the sign is changing each time. Negative x goes to x squared goes to negative x cubed, negative x cubed goes to positive x to the fourth. So we need to represent that with a negative x there. But again, what does our power need to be? Well, look at your pattern. X to the 0 is like our first one. X to the 1 is there. X to the 2 is there. X cubed is there. So again, compare that to the term number. Well, 0 goes with 1. 1 goes with 2, 2 goes with 3, 3 goes with 4, etc., etc. At each stage of the game, the value of the exponent is 1 less than the value of the term number. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3, etc. So we're going to write that as n minus 1. And again, test yourself, make sure this works for your terms. Like what happens if you just plug 1 in, for example, for the first term. Let's make sure it works at least for that one. Holy moly, if it didn't work there, we're going to be in trouble. So we're going to get negative x times 1 minus 1. Well, 1 minus 1 is 0. So I'm going to get negative x to the power of 0. over 1 minus 1 factorial. Let's simplify that. Anything to the power of 0 is 1, and 1 minus 1 is 0, but 0 factorial is defined as 1. So we're good. We got our first term. And we're going to stop right there because since this is not geometric, we cannot find the sum. So there you go. There is your general formula for a term of this infinite series.